Okay, good morning to everyone. Thank you, Mr. Bai. Today we will speak about some numerical models for the robustness assessment of reinforced concrete frame buildings. Before to face the technical aspect of this issue, let me summarize some historical aspect about this phenomenon, this problem. First of all, a milestone in this field is represented by the collapse of RONAN Point apartment tower. This structure was built with precast concrete elements and had 22 stories. The cause of the collapse was a gas explosion in a kitchen at 18th floor, which destroyed the one of the load bearing wall. So the structural portion placed above of the 18th floor lost the support, and like an hammer, causing the collapse of all the entire corner placed below the 18th floor. This is a milestone because this collapse highlighted some lacks into the guidelines and into the structural code at the times. Now, I reported two examples in which the presence of adequate requirements for structural robustness or the lack of adequate requirements made the difference. The first is the ALFRED MURRAH Federal Building, a structure made with a reinforced concrete frame of 9 stories. That was attacked with a truck bombing in 1995. Here we have a picture of the structure after the attack. Certainly, we cannot compare a truck bombing with a gas explosion in a kitchen, but there were some critical issues that played a crucial role in the definition of the structural response after this event. In particular, as you can see from this picture, there was a transfer beam at the 3rd floor that was a critical element. In addition, this structure was not designed to withstand an earthquake, and there was the absence of continuous ties in the beams and the absence of any alternate load path. Another critical issue is represented by the absence of security fences. While about some examples regarding the case in which the provision of adequate requirements for structural robustness made the difference in the structural response, I have decided to report the case of the Pentagon. We have a structure in a reinforced concrete frame of 5 stories that in 2001 was attacked with a Boeing 757 that impacted against the west facade of the building, destroying suddenly 50 columns. But if we consider the portion of the structure that was not directed, interested by the attack, we can see that the structure remained stable for at least 20 minutes, and it was very important because this allowed workers to run away. Here we have a picture of the site after the removal of the debris. And in the definition of the structural response, there were some decisive factors. First of all, the provision of an alternate load path. And then also other provision, like the use of short span, the provision of continuous bottom ties in the beams, and the use of some requirements in order to improve the ductility. As an example, the use of spiral stirrups in the columns. There are a lot of definitions about the structural robustness. I have decided to report two of these definitions. One is given by the Eurocode 1 in the section 1.7. That states that robustness is the ability of a structure to withstand events like fire, explosion, impact, or also the consequences of human error, without being damaged to an extent disproportional to the original cause. Another definition is given by Canisius that says that robustness is a property that makes buildings not suffer disproportionate collapse, including progressive collapse. So we have these two terms, disproportionate and progressive, that sometimes are used like synonyms, but that have two different meanings. In fact, in a disproportionate collapse, the structure can be damaged as a consequence of an accidental action, is quite obvious. However, the damaging must be proportional to the original cause. While a progressive collapse is a kind of type of failure similar to what happens in NAS or cars or with the dominoes, where structural elements collapse one after the other. About the design against accidental situation, the Eurocode defines two families of strategies. One family is based on the identification of the accidental action, and another family of strategies is based on the limitation of the extent of localized failure. The designer can reach this aim following different ways. The first is by enhancing the redundancy, for example, by providing alternative log paths. Another is by designing the element as a key element, able to withstand the notional accidental action defined by the code, or by applying prescriptive rules. For example, by improving the structural integrity, the ductility, and so on. In Eurocode, there are also some requirements in terms of horizontal and vertical ties, because the code established that all the elements of the frame must be tied together. So there are a minimum amount of these ties. And for the horizontal ties, these are a function of the transversal span, the longitudinal span. We can see the S that is span in longitudinal direction and in transversal direction. And also is a function of the dead load acting on the structure, and also of a portion of the live load acting on the structures. About the vertical ties, the Eurocode established that each column should be tied continuously from the foundation to the roof level. The code established also an admissible damage in terms of area, and this is an important requirement for the designer in order to evaluate if the structure has a sufficient level of structural robustness or not. When the designer has to check this requirement, first of all, he has to define the consequences class of the building. Currently, we have 4 different consequences class, but if we exclude the class 3 that requires a systematic risk assessment, the class with the stricter requirements is the class 2B. And practically, the designer, first of all, must provide the effective horizontal ties in the structure. Then he must check he has to apply the accidental action on the building, and he has to check if the structure remains stable, and if the damaged area exceeds the limits seen before. If this area respect the limits seen before, the designer provide the horizontal and the vertical ties, and the requirement is satisfied. Otherwise, he has two ways. The first way is to design the elements like key elements. While another way is to apply the notional element removal strategy. Practically, the designer must remove one at a time in each story, each supporting column, each transfer beam, if present, and any nominal length of the load-bearing wall present. Then he check the stability of the structure, check the amount of damaged area, and if these requirements are satisfied, the structure can be considered sufficiently robust. Otherwise, he has to design the element as a key element. Here we have the definition of the national element removal strategy by Eurocode. But the question is, how can I simulate the column removal? And then, when the removal can be considered quasi-static and when can be considered dynamic. But also, should the designer consider only the frame's contribution in the analysis, or the presence of the floor system can change the response? These are only some of the question of my question when I started to apply my research activity to these fields. To give you some answer, I decided to report some the results of some experimental tests. The first regards to the beam column sub-assembly in area scale, and was tested and developed at the National Institute of Standards and Technology. Here you can see a picture taken at the end of the test. The engineers used 4 hydraulic jacks placed below the strong floor of the laboratory to pull down the central column in order to simulate the quasi-static removal. They used also other measures in order to reproduce the actual condition of the frame. As an example, they use this device, these roller fixtures, in order to place in the position of the contraflexural point. They use these beams, these vertical steel beams, in order to avoid out-of-plane displacements. And they use also some steel plates that are not visible but are placed in this position along the columns in order to reproduce the actual anchoring of the bars by means of a mechanical anchoring. In this picture, we have a plan view and an elevation view of the building, of the actual building, and the location of the sub-assembly. Here we have some details of the geometry of the specimen in terms of cross-section, arrangement of the reinforcement, and also the arrangement of the sensor placed on the structure. We have some inclinometers, some load cells, some LVDT sensors, and also some strain gauges, and so on. Here we have some information about the reinforcement, the compressive strand, the tensile strand of the concrete, and so on. The behavior can be summarized by monitoring the trend of the force applied by jacks, the vertical displacement of the point P1, and the horizontal displacement on the point P2. And this behavior is summarized into these two graphs. In the first graph, we have the trend of the applied force as a function of the P1 vertical displacement, while in the second graph, we have the trend of P2 horizontal displacement as a function of P1 vertical displacement. We can subdivide this behavior into 4 different phases. In the first stage, we can see initially an uncracked phase with elastic stresses. Then we can see progressive cracking with the stiffness reduction up to the reaching of the ultimate flexural bearing capacity in correspondence of the progressive yielding of the beam reinforcement near the columns. I did not report the trend of the axial force in the beams, but in this part of the analysis, there was a compressive axial force in the beams. About the trend of the point P2 displacement, we can see an upward displacement given by the negative value. The compression that we have in the axial force in the beams is given by the cracking of the beams. This cracking causes an elongation of the beams, but this elongation is partially prevented by the flexural stiffness of the columns, and so compressive axial force arises in the beams. If we continue to pull down the central columns with the use of the hydraulic jacks, we can see that there is a stage in which we have the plastic hinges development, and this is due to the yielding of the steel bars in tension, and also due to the concrete crashing in compression. This causes a reduction of bearing capacity, as you can see from the first graph, and also a reduction of compression in the beams. About the displacement of point P2, we can see that in this phase, the point P2 reverses the trend up to the reaching of a zero condition. In the third stage, we can see a recovery of the load bearing capacity and an inward displacement of point P2 up to the reaching of an asymptotic value. In this phase, there is the switch of the tensile of the axial force in the beams from compression to tension. Finally, if we continue to pull down the column, we can see that the tensile stress increases in the beams, and there is the complete development of the catenary action. So now we have the complete switch from the flexural behavior to a tensile one. And as you can see, there is a big increase in load bearing capacity that exceeds the ultimate flexural one measured in the earlier stages of this test. In this slide, I summarized the evolution of the behavior. Practically, we have three different stages. An initial stage in which the loads are transferred by exploiting the flexural resources of the frame. A second stage, featured by the development of the plastic hinges with a reduction of bearing capacity. And then we have a final stage in which there is the development of the catenary action. This was a case of quasi-static removal. If we consider instead a dynamic removal, I reported the results of another experimental test developed and tested at the Nanyang Technological University. Here we have a picture of the taken during the test and a detail of the quick release device. Here we have some details about the layout of the test, some information about the geometry, the cross-section, the reinforcement arrangement, the material strength, and so on. And in this slide, I have decided to report three different graphs. In the first, we have the trend of P1 vertical displacement as a function of the time. In the second graph, we have the trend of the total vertical reaction measured at the level of the external column. And finally, in the third graph, we have the trend of the horizontal reaction. And this is very important because it gives us some information about the development of the catenary action in the beams. We can subdivide this behavior into two main stages. We have a first transitional stage in which the point P1, that is the point located in correspondence of the central column, is increasing the vertical displacement up to the reaching of an equilibrium condition. If we look what happens at the total vertical reaction, we can see the load is progressively transferring to the external column. Then there is a phase of stabilization, but when the frame reaches an equilibrium condition, it stops the evolution, and we can see the effect of the given by the dynamic amplification factor. In fact, if we compare the tendency value reached at the end of the test, that is more or less 35 kilonewton, and we compare this value with the maximum value reached, that is more or less 65 kilonewton, we can see an amplification factor of more or less 2. While if we look what happens in the beams, we can see that initially the beams are subjected to compression, but then there is the switch to tension, and the beams remain in tension for all the rest of the test. Then we have the second stage, that is a damped free vibration stage, in which the beams oscillates around the equilibrium position, dissipating the stored energy. About the answer regarding the third and the fourth question, regarding the 3D effects of the structure, I have decided to report the results of this study. This is a very interesting study developed at Nanyang Technological University, and it regards a 1/4 scaled system made by beams plus a collaborating slab. This is a very interesting study because the engineers developed a series of specimens that represents an evolution of the structure. Here we have some details of the system used to apply the load, and also a detail of the system used to restrain the specimens. Practically, first of all, the designer tested the behavior of the P-series specimens that are made with only the transversal beam. Then they tested an evolution of this structural system made by coupling the transversal beam with the longitudinal beam. And finally, with the S-series specimens, the engineers tested the behavior of the global 3D structure made by beams plus the collaborating slab. Here we have some details about the geometry of the structure and about the materials. This slide is very interesting because I reported the results obtained with all the specimens, and the red curve is referred to the system made only by the transversal beam. The blue curve is referred by the system made by the transversal beam plus the longitudinal beam, while the green curve regards the 3D, the total 3D model. As you can see, by considering the effects of the 3D effects, we have a stiffer global behavior represented by the slope of the first part of this curve, and also a Eiger ratio between the ultimate force applicable by the system, the device used to apply the load, and the force applied in correspondence of the yielding. So I have reported this table with all the results obtained for each specimen, and also some ratio between the different specimens. A difference between the blue and red curve, if compared with the green curve, is that while for P1 and T1 specimen we have only the resisting contribution given by the compressive arching action and then tensile catenary action, in the P1 specimen we have also the contribution given by the slab. So in the first stage we have the contribution given by the compressive membrane action, while in the final stages of the test we have also the contribution given by the tensile membrane action. After this, up to now, we have seen only the results given by some experimental tests, but my question was if the commercial software are able to reproduce this kind of behavior. So I decided to use Diana, in particular in the version 10.1, to develop some static time history nonlinear finite element analysis. Here I have reported some details about the finite elements that I have used to reproduce the test, and in particular I used beam elements to reproduce the beams both in P series that in T series and S series specimens, while I use shell elements to reproduce the behavior of the collaborating slab in S-series specimens. I have developed a calibration procedure in order to avoid some mesh dependency problems, and after this calibration procedure I define the mesh size for the shell elements, and in particular I use the element with a size of 5 centimeters. About the reinforcement, I decided to model directly the reinforcement in the model by use the bar elements that are embedded into the beam elements. About the materials, the concrete has been modeled by use the law defined by the model code 90, and if you look on the right side of this slide, you can see an extrapolation of the DAT file with the definition of the materials, and I made some modification to the model proposed by the model code because Diana allows the user to make some changes, for example about the evolution of the Poisson coefficients due to the damaging of the structure, or about the behavior of concrete subjected to compression, or the reduction of the concrete strength due to cracking, and so on. While about the steel, I used bilinear law with hardening branch, both in tension that in compression. About the restraints, I modeled this device used by the engineers to restrain the actual specimen, and I have coupled the centroid of the shell elements with the centroid of the beam element by means of some rigid links. About the analysis, here I have reported an extrapolation of the SGC file. In the first part of this file, I have defined the type of the analysis. In particular, I have defined a linear geometrical analysis. In the second part of this file, I have defined some information about the iteration method, that is the one defined by Newton and Raphson. Some information about the convergence criterion, that is based on the displacement control, and also the time step execution. And other information. While in the last part of this file, I've defined the output definition in terms of stress, strain, cracks, and so on. Here, I have reported the results obtained for each specimen. Now I start with the simple model, the P1 model that is made only by the transversal beam, as you can see in the picture placed on the bottom left side on this slide. As you can see from this graph, there is a good accuracy between the experimental results reported with the black line and the numerical results that are reported with the dashed black line. The accuracy is good for all the duration of the test. On the right side, I have reported two pictures. In these two images, there are represented the axial force in the reinforcement, both in the bottom reinforcement that in the top reinforcement. And as you can see, in the first stage, we have flexural behavior given by the traction in the bottom reinforcement, the tension in the bottom reinforcement, and the compression in the top reinforcement in the section placed near the central column. While in the last stages, you can see that the bottom reinforcement are totally in tension, and this highlights the development of the catenary action. Here we have the results about the specimen T1. As you can see, there is a very good accuracy for all the duration of the test, but we have a difference regarding the ultimate displacement reached by the experimental test and the ultimate displacement reached with the numerical model. But you have to consider that, as you can see from this picture, from the picture placed in the bottom left side of this slide, during the test there was a shear failure. And after the shear failure, the test was stopped. Clearly, the shear failure is a kind of collapse fragile, and this is more difficult to be reproduced with this kind of analysis. But if we look what happens in the correspondence of the shear failure, you can see a drop in the resistance of the specimen, and so this is in a certain way an information about the loss of bearing capacity of the specimen. About the specimen S1, that is more complex if compared with the previous ones. You can see that we have a good level of approximation. Here we have some differences in terms of the reproduction of the correct cracked stiffness evolution, and there are also some differences in the evolution of the behavior for large displacement. But as you can see, the software is able to reproduce both the phase of the plastic hinges formation development, but also the behavior in correspondence of the ultimate condition. That is very important for this kind of analysis. Here we have a picture taken from the test, and as you can see, there is a detachment between the beam and this slab, and surely this problem has influenced the results. So as you can see, the answer to the question about the floor system contribution is obvious. The improvements in terms of structural response can obtainable by considering the floor system contribution cannot be neglected. But the real question, the actual question is, how can I consider the floor system contribution? Because if you imagine to model the floor system with shell elements for all the floors of a structure, even if the structure has only 3 or 4 floors, the number of finite elements that you have to manage is too big. So this means too long pre-processing times, too long post-processing times, slower analysis, problem with stability of the analysis, and so on. So my question was, how can I consider the floor system contribution in a simplified way? And the idea was quite simple. I started from the results obtained with the S1 model, and I tried to develop some simplified models. First of all, I exploited the double symmetry of the specimen. So you can see 2 symmetry axes, the AA axis and the BB axis, and I have applied some restraints which reproduce the symmetry conditions along these two axes, and the idea was to substitute the slab, the original slab made with shells, with a girder made with equivalent beams in each direction. The equivalent beams is given by the actual beam placed in this position. We have also an half of beams also in this position, plus the collaborating slab. But so we have 2 elements in horizontal direction and 2 elements in a vertical direction. But in this way, we have a portion of the structure that is unmodeled. So I decided to test an evolution of this simplified model, and I developed the EB2 model, which consider the introduction of a further element in each direction. Here we have some problem with this image. Here there is a dashed line similar to this one, and also here there is another dashed line similar to this one. But then I decided to test a further evolution. So I defined the model EB3, that is an evolution of the EB2 model with the introduction of a further element in each direction. And so now we have this layout. So we have 4 elements in vertical direction and 4 elements in horizontal direction. Each element has this cross-section. So we have this T-shaped cross-section for this element, 2 rectangular cross-section for these other elements, and a half T-section for these elements, and a similar discretization also for these other elements. And now I will show you the results achieved. Practically, I have compared the results obtained with the experimental model, that is the red curve. That is the results obtained with the S1 experimental model, the black curve of the graph that we have seen before. And I've compared the results of the model EB1 also with the results obtained with the shell model that now is represented with the green curve, but that before was represented by the black dashed line curve. As you can see, there is always an overestimation of the cracked stiffness, but this is similar to the overestimation obtained with the S1 function model. But we have an improvement in the definition, the estimation of the maximum flexural load. While if we look what happens in the advanced stage of the analysis, there is a loss of accuracy both in the simulation of the post-yielding stage, but also in the there is an overestimation of the load carrying capacity in the ultimate stage. This is a picture of the axial force in the reinforcement during one of the stages. About the model AB2, as you can see, we have obtained a great improvement in terms of results. We have a similar behavior to the AB1 model in the first stage, but we have a great improvement in the post-yielding stage and also in the ultimate stage. But we have still a part for a vertical displacement between 150 millimeters and 250 millimeters, more or less, in which there is an unstable behavior. So we decide to evaluate the behavior obtained with the EB3 model. As you can see, we have a similar behavior if compared with the EB2 results, but now we have a better and more stable behavior in this region. So at the end of this approximation, I decided that this kind of approximation was sufficient to properly reproduce the behavior, especially if compared with the results obtained with the shell model. Here we have a picture of the stresses during one of the stages in the reinforcement. If you consider the results achieved, and if you imagine the simplification obtained by substituting the shell elements of the slab with a limited number of beam elements which compose the girder, you can have an idea of the time saved both for pre-processing phase that for post-processing phase, and also of the reduction of the time spent for the analysis. So in conclusion, I can say that Diana is able to simulate the structural behavior even in case of large displacements and rotations, and this is confirmed by the accurate way to reproduce both the flexural behavior that the catenary reaction, both for 2D that 3D frames. And about the simplified models, I can say that the simplified models proposed, especially the simplified model EB3, can be considered suitable to reproduce the resisting and the stiffening contribution given by the slab. This means a lot of time saved in terms of pre and post-processing phases, and also faster and more stable analysis. In this slide, I give you some references if you are interested in this field, and thank you.
Oh, thank you very much, Dario, for your presentation. Now we'd like to have a Q&A session. Anyone who has a question or discussion, please write it down in a question dialog box on your webinar control panel. If you'd like to use your microphone, please let me know.